My name is Will Happer. Let me see if I can get this thing to work. Let's see. Okay, got it. The title of my talk is More CO2 Benefits the Earth. I'm from Princeton University. I'm professor of physics there. I've been there since 1980. Before then, I was at Columbia University for many years, and I also served as Director of Energy Research under President Bush Sr. at the Department of Energy, so I had all the non-weapons basic research of the Energy Department, including climate, and that's where I first really got interested in some of the oddities of this branch of science. So we've heard that CO2 is sort of the demon molecule because it causes global warming, catastrophic global warming. Certainly if you live in a place like I do, temperate New Jersey, I wouldn't mind a few degrees of warming. I was a kid in Scotland, and I can tell you that most Scots would really love to have a little warmer climate. But that aside, we've had a lot of time now to look at how well scary models work. They don't work. They've all predicted much more warming that actually has occurred. The warming will be very beneficial, as was already alluded to in the introduction, and you can actually already see the planet greening from space. There are clear evidence of that. So what do we do to stop this hysteria? Well, people have different views, probably different strategies work for different people. Many people have tried defense that warming won't be so bad, don't worry about it. It's a necessary evil, we've got to have fossil fuels. And another strategy is collaboration. Well, let's put on a good face and show how we're minimizing our carbon footprint. I don't know why you'd want to do that, actually. But many industries have done that. I think they're beginning to regret it and realize it was a bad strategy. So I think that the right procedure is to be offensive, is to tell the truth. The nice thing, it is the truth, and that is that more CO2 will benefit the Earth. So just a few words of introduction of myself so that I can try and claim some authority here. I was the co-author of one of the first books on global warming. This was written in 1982. So here I am, but there are a number of impressive people on it. There's Bill Nierenberg, who was the director of Scripps Institute of Oceanography, Walter Monk, a distinguished oceanographer. And we predicted warming from CO2, and I have to confess with some shame that actually we predicted much too much warming. I'm one of the few who's willing to admit that we got it wrong. But I've been in this business for a long time, but it's not what I'm most noted for. I'm actually most noted for the invention of this gadget, and this is called the sodium guide star. If you go to any modern telescope, you'll see this yellow laser beam pointing to the sky to where the observed galaxy or stars are located. And this is something I invented in 1982. It was heavily classified for 10 years, but here's a little description from a book about the topic at the Jason 1982 summer session. Will Happer from Princeton presented the revolutionary concept that the mesospheric sodium layer could be used to generate high-altitude artificial guide star for use with adaptive optics, et cetera, et cetera. So this actually works. It's unlike climate models. Actually, mine worked. Theirs don't. And neither did my climate model work either, for that matter. So anyway, I know a lot about the atmosphere, and that was why I was able to make this suggestion. And so let me now go tell you some more about the Earth's atmosphere. We're talking about the CO2 molecule. That's what it looks like roughly. It's an artist's conception. If I'd drawn this, I'd have made the carbon a little smaller, but the black is carbon and the two red things are oxygen. So it's very similar to a xylophone bar. It will bend and vibrate. And the main vibration that is talked about in global warming is this bending vibration here, where the carbon moves up and the oxygens move down. And this puts out radiation that has 666 waves per centimeter. You notice it's like the biblical number, Satan's number, 666. So there's no doubt that this is a dangerous frequency. There are other frequencies too. The box oxygens can move in and out, or they can move in an asymmetric way in and out. These don't matter much for global warming, these axial stress, these axial vibrations. The main one is the bending vibration here. And of course, this molecule is not only bending, but it's spinning round and round in space, and that is what makes the absorption band that everyone is so worried about. Okay, but it's not a pollutant. You know, if you look at our breaths, if you look at this room, I used to, when I would lecture in Princeton, I would bring along a CO2 meter, and you would typically measure in a room like this 2,000 parts per million. You know, the outside air is 400, so it would be typically 4 or 5 times the outside air, because everybody was breathing. If you want the CO2 to go down, you have to stop breathing. And most people don't want to do that. And you breathe out a lot, actually. Each of us breathes out roughly 2 pounds of CO2 per day, 2 pounds per day. And you think, why don't I lose weight faster, you know? You might think about that for a minute. I'll come back to that, explain. Okay, so it's CO2. But anyway, the point about this is that a coal power plant and a person are emitting essentially the same thing, mostly water vapor and CO2. People breathe out more oxygen than a coal plant. A coal plant, you're trying to burn as much oxygen as you can, you know, get the maximum heating rate. But they're very similar. And if in a modern coal plant, what actually comes out of the stacks, aside from the water vapor, was what you see here from the stack and from the cooling towers, is essentially the same thing that comes out of a person's mouth on a frosty day. So CO2 is not a pollutant. This is the Turk supercritical power plant in Texarkana, Arkansas. I was there just 2 or 3 weeks ago, and one of my colleagues, Norm Rogers, took this photograph. There's the stack. This is running full bore. You can't see anything coming out of the stack. You can see the steam from the cooling towers here. And the flame is in this tall building, and everything between there and here is emission control technology. So it strips out all the sulfur, all the oxides of nitrogen, all the particulates, so nothing comes out this chimney. So this really is not so different from your own breath. You don't see anything coming out there. And you can build plants that way. The real problem with coal right now, of course, EPA is just completely bonkers, but the serious problem is that natural gas is so cheap that if you're a utility board member, you'd be crazy to order a coal plant when you can get a natural gas plant at 1/3 the cost. So that's the problem for coal now, if you forget about regulations. Okay, so I mentioned the carbon that we breathe out, you know, our own carbon footprint, and the reason so much carbon is there, we're made mostly of carbon. If you look at the composition of an average human being, the largest by mass is oxygen. That's because of all the water in our body. But the second is carbon, and that's because most of the tissue that is built into us is made of various molecules of carbon. Hydrogen is third. That's because it's water again, oxygen and water. And finally, there are smaller amounts of nitrogen and other elements. So it's an eye chart, but the takeaway message is we're mostly carbon if you forget about the water. So life is based on carbon. Why do we want to eliminate the carbon footprint? You know, please don't answer. Okay, so, and where is the carbon in the body? This is why it's so hard to lose weight, by the way. Most of it's at least half of it is in fat, and roughly the other half is in protein. There's a little bit in sugar, the glycogen in our own bodies. But fat is almost pure carbon. It's got a little bit of hydrogen, 2 hydrogens per carbon. And so this is a fatty acid, typical of what's inside us. These are proteins that build our muscle, enzymes, and other chemical factories inside of our body. They also are full of carbon. These black dots are carbon atoms, but there's more of other things in protein. There's a lot of nitrogen in protein. There's even sulfur. And so the reason you lose weight so slowly is that CO2, most of the weight of CO2 is from the oxygen that you inhale. You know, so for every carbon, there are 2 oxygens that came from the air. So only about a third of that 2 pounds of CO2 came from your fat. And so that's why it's hard to reduce by breathing 2 pounds of carbon a day, carbon dioxide a day. Okay, so what about global warming? Are we going to fry from increasing CO2? The answer is certainly not. Life will flourish more abundantly. And let's get into the key atmospheric physics here. I know Tim Ball is going to say a lot more about this, so I'm going to be brief. But the first thing to remember about the atmosphere is that it doesn't have a single temperature. The temperature is maximum at ground level, so this is altitude going up, and this is temperature left to right. And the temperature drops very rapidly as you go up. You can see here in Arizona, if you look at the newspaper I checked this morning, Flagstaff is approximately 20 Fahrenheit colder. There's frost up in Flagstaff than Phoenix, and that's true just about every day. And that's this lapse rate you see here. That's true everywhere in the world. So the atmosphere cools up to about 10 kilometers, 35,000 feet. That's the beginning of the stratosphere. Then it actually warms again as you go higher because of absorption of ultraviolet light from the sun. It gets almost to the temperature of the surface here at 30, 40 kilometers. And then it cools again when you run out of atmosphere to heat. So that's the vertical structure of the atmosphere. And on top of that, there's enormous circulation patterns in the Earth. This is greatly simplified, but roughly, most of the sunlight is in the equatorial regions. That's where the sun is mostly overhead. There's a lot less sunlight at the poles. And so the Earth is being heated mostly at the equator, and that heat is carried north and south by these huge convection cells. And the first cell is called a Hadley cell, and it rises up at the equator, dries out because of the heavy rain, and then the dry upper atmospheric air falls down at about 30 degrees latitude, which is Phoenix. So we're sitting here at the bottom of the Hadley return cell. That's why it's so dry in Phoenix, is that the air has been stripped of all the moisture it got at the equator by being cooled in the upper atmosphere. So there's a desert belt that runs around 30 degrees north and 30 degrees south. The Sahara is sitting in that belt, and the Sonoran Desert where we are now. And then there are additional, even more complicated convection patterns that carry heat poleward and cold southward. Wish it would stop. Okay, and so roughly speaking, this is the energy budget of the Earth. We're heated mostly by the sun. There's a tiny amount of heat coming under our feet from the interior of the Earth, but that's less than a part per thousand of the sun energy. And some of that energy, all of that energy eventually goes back to space. And so this is actually from NASA. And in principle, there's nothing wrong with this diagram. The devil is in the details. The problem is they've massaged a lot of small numbers to make this perfectly normal and acceptable physics into something that's scary if you add a little CO2. It's just not true. So let's talk a little bit more. I've tried to stick to facts here. This is one of the few sort of theoretical things, but this is based on good measurements. But the escape of radiation from the surface of the Earth back into space is hindered by a number of molecular gases. The most important by far is water vapor. So here's water. And so what I'm showing here is wavelength of radiation. I think you know you can see visible radiation with very short wavelength, less than 1 micron. Longer radiation you can't see, but you can feel if it's hot enough. You can feel that fire feels nice and warm. I can feel the radiation. And that radiating heat is hindered by water vapor, carbon dioxide, which is second by far. This is the absorption by carbon dioxide from ground to space. There's actually absorption by oxygen and ozone, a little bit by methane, nitrous oxide, etc. And of course, there's the blue Rayleigh scattering of the sky. That doesn't deposit heat, but it keeps sunlight from reaching the Earth. Now, here's what you actually see. If you go up and put an instrument in a satellite and you measure radiation coming out, here's that same radiation. Unfortunately, now it's left to right instead of right to left. So this is decreasing wavelength, increasing frequency to the right. But you can see that the radiation in the region of the CO2 absorption over most of the Earth is less than it is where the radiation is not absorbed. So this is unabsorbed radiation that can get to space directly from the ground if there are no clouds. Usually there are clouds that, is the least understood part of all of this. So this is the Sahara Desert. You can see the ground is very hot, 320 Kelvin, that'd be about 100 degrees Fahrenheit. Here's the Mediterranean, just 100 kilometers north, and it's quite a bit cooler because the Mediterranean water keeps it cool. Again, you see less radiation where the CO2 band is, but a lot of absorption from water. So most of suppression of radiation reaching space is from water. And I should also say that adding CO2 almost makes no difference to this band. It's easy to do these measurements, and all it does is it makes this CO2 band just slightly broader. It doesn't make this any deeper. So that's one of the problems the alarmists have. If you actually honestly model it, it's very hard to get warming that would worry anyone. So they've invented all sorts of positive feedbacks that probably don't exist. One of the most interesting regions is the South Pole. So this is looking down on a cloud-free day at the South Pole, Antarctica. And there you see actually CO2 has the opposite sign. It increases the cooling of the Earth. So if it were not for CO2, the Antarctic would be a little bit warmer than it is. So CO2 is acting as a cooling agent at the poles. Warming, okay, I may have the sign wrong. Getting the sign right's the hardest thing, as I said to begin with. Now CO2 is increasing. There's no question about that. This is measurements at Mauna Loa in Hawaii. And you can see this is the interval 211 to 216, 2016. The CO2 increases dramatically during the winter. That's because there's no photosynthesis during the winter. And when spring comes, there's a rapid drop. So CO2 actually decreases through the spring and summer to a minimum in the late summer, early fall. That's because all the northern hemisphere plants have sucked out a lot of CO2 to build plant tissue and wood and all these other things. And here's another version of the same curve. This is a little harder to understand, but this is the latitude on Earth. So this is the North Pole, this is the equator, this is the South Pole, and this is year going this way. These graphs are a little hard to read, but anyway, you can see the fluctuation up, down, summer, winter, summer, winter. They're enormously large up in the tundra, the Arctic tundra, where there's a lot of growth during the summer. There's a lot less in the southern hemisphere because most of the southern hemisphere is ocean. There's not much land. Most of the land of the Earth is north of the equator, and that's where the land plants work. And also the southern hemisphere phase is opposite. Summer occurs during our winter. So the peaks and valleys are opposite in the south than from the north. Now, I mentioned the models aren't working. I hope Tim Ball will say more about this. I'll just briefly pause on this. This is the average of lots of models of what the temperature rise should have been from 1975 until 2025. And these are observations, and you can see there's an increasingly embarrassing gap between observations. Here we are at 216. It's really pretty serious, very, very mild warming. And nobody knows how much of this is due to CO2. Maybe most of this is natural. But the models are unambiguous that there should have been much more warming than we have. So the models aren't working. This is from testimony by John Christie. Just a mea culpa, that was my estimate of the warming in 1982 with my Jason colleagues, and we got it wrong too. We were estimating about 0.3 degree per decade. In fact, what's been measured, this is a version of Christie's data, but this is published in Nature, so it must be right. And again, the bars, the gray bars, are model predictions, and the red is what's observed. So what's observed is much less warming than what's predicted. So that's the takeaway message, is that all of the alarm is based on models. The models don't work. So get serious about this, guys. So here's a typical temperature measurement. This is from satellite measurements by Roy Spencer and his colleagues at University of Alabama, Huntsville. And you can see that this is temperature and this is year. Starts at the beginning of the satellite era, 1979, when our first measurement satellites went up, to today. And I just downloaded this a day or two ago, so this is the data through November. And over this entire span, the warming has been very, very modest compared to predictions. And you can see these huge fluctuations year from year. We were just coming out of a huge El Nino in the Pacific, and so we're cooling down now. I expect this cooling to continue, but I can't forecast the future. You can see what happened with the last big El Nino in 1998. Big spike in temperature and then rapid cooling during the La Nina that followed. So there is, as satellites observe it, a small amount of warming. It's much, much less than predicted, and nobody knows how much of that's due to CO2. Probably no more than half is my guess. I mentioned El Ninos, which have such an enormous effect on climate, and in case you don't know, the way that works, this is the Pacific Ocean, and this is depth under the Pacific Ocean. Here's California, here we are in Phoenix up there. And during El Nino, all of the warm water that's normally sitting off the coast of Australia and Indonesia sloshes back east to the coast of the Americas, and so the whole surface of the Pacific gets much, much warmer than it normally is. And so that makes the whole Earth look warmer, because this warm water, which is normally hidden at great depths off Australia, is suddenly exposed, and you see it as part of the surface temperature of the Earth. We're now entering a La Nina, sort of the opposite phase of the El Nino we had last year, and this water's being pushed even further westward, and so the Earth is cooling because of this phenomenon going on right now. So we're in the middle of a La Nina, just getting started. So last night, just before I went to the reception, I downloaded this picture of the Earth from a geosynchronous satellite. You can look at it yourself. But this is the visible light coming from the Earth. If you look very closely, Phoenix is up here, and so it was just getting dark, so we're in the shade of the approaching night. It was still light out over the Pacific. So the takeaway message I want you to get from this is that if you look down at the Earth, you only see it in the visible if it's daylight, And what you see mostly is not the surface of the Earth, but clouds. So the Earth is covered with clouds. These clouds have a huge effect on the warming and cooling of the Earth, and nobody really understands them very well. And clouds are very different depending on whether they're high clouds or low clouds. And I'll show you that in the next image, which I also downloaded last night. So it was the Earth last night at about 6 o'clock here, Phoenix time. So now this is looking at long-wave infrared, 10 microns from the same satellite. And you can see it was partly cloudy over Phoenix. You could see the stars last night, but there were clouds. And now what you're looking at is the glowing of the Earth in the infrared. And so the darker this is, the more heat radiation is coming out of the Earth to space to cool the Earth. And the whiter it is, the less. And so the interesting thing here is these white areas are clouds. So the tops of clouds are very cold, so they don't radiate very well. So the thing that makes clouds especially complicated is that very high clouds, these white clouds here, which are very high, tend to warm the Earth because they don't let it cool as efficiently. They're poor radiators when they're cold. But low clouds are very strong cooling mechanisms because they reflect the sunlight. You don't see it here because the sun isn't shining. It's nighttime here. But these are clouds off the Pacific, and the cloud tops of these big stratus layers in the Pacific are almost the same as the open water. So they're radiating very strongly to space, cooling the Earth, but they don't let any sunlight come in to get converted into heat. And so low clouds cool, high clouds warm. Okay. Now, I don't want to run out of time, so let me quickly come to the punchline. So more CO2 will be a huge benefit to agriculture. When I'm in the East, I often ask my liberal academic friends, what crop is this? And most of them haven't got a clue. I presume most of you in the audience know what this is. Soybeans, right? Yeah, my friends, when I ask them that, they say, is it marijuana? And no, I say, yeah, I know what marijuana looks like. It doesn't look like this. Okay, so now plants are really struggling at these low CO2 levels. Let me explain why. The most abundant protein, I mentioned proteins not long ago. The plants are full of proteins too, just like us. And the most abundant protein by far is called rubisco. It's the enzyme that converts carbon dioxide to sugar in plants. So there's more of this than anything else in the world, on land plants and, in the algae in the sea, And it was designed when there was practically no CO2 in the air, probably, more than 3 billion, maybe almost as long as 4 billion years ago. And so when it was designed to convert CO2 into sugar, for sure. That was its function, but there was no oxygen. And it turns out there was a design flaw, and this miserable molecule gets confused by oxygen. So if there isn't enough CO2, which is true today, and there's lots of oxygen, which is also true today, about every fourth try, instead of grabbing a CO2 molecule, this rubisco grabs an O2 molecule, and instead of making useful sugars, these are very primitive sugars that are being made, it makes toxic substances, among them hydrogen peroxide, which is very bad, for the plant. You wouldn't want to drink hydrogen peroxide either. And so the plant is full of all sorts of detoxification mechanisms to handle this, what's called photooxidation, that it's picked the wrong molecule and it's caused harm instead of good. So one of the reasons that more CO2 is helping the Earth so much is that if there's more CO2, then the plant doesn't make this mistake as often. So it doesn't have to pick an oxygen because there's more CO2 available to work with. And plants have known about this problem for a long time. This is an example of evolution in action. Corn and sugarcane are a few of the plants, commercial crops that we use that are adapted to low CO2 levels. And the trick that corn uses and sugarcane uses is it takes the CO2 from the air and it ferries it chemically to a protected region within the leaf of the plant where the rubisco is, this enzyme that's poisoned by oxygen. So it protects the rubisco, but at the expense of having to develop all this biochemical machinery to ferry the CO2 through these impermeable barriers to where it's converted to sugar. Most plants, most of our agricultural plants use the old-fashioned thing where they don't try to cope with the low CO2 level, and so they're stuck with this oxygen poisoning. It's hard to think about it, but as far as a plant is concerned, oxygen is poison. CO2 is good, but oxygen is poison. Okay, here's some pictures of actual stomata. These are the little holes through which CO2 diffuses into the plant interior, the interior of the leaf. This is one of the ways that you can infer past CO2 levels. This is a leaf that was dug out of a bog, I think in Denmark. No, I'm not sure, somewhere in Northern Europe. And it's a fossil leaf. And if you count the number of stomata in the leaf, you find that the number changes over time. Very old leaves tend to have fewer stomata. And that's important because this stomata that I mentioned, not only does it let CO2 diffuse in, but it lets water diffuse out. So the plant has this engineering trade-off it's had to make. It has to have these holes in its leaf to get the CO2, but the holes let water leak out. So plants are real hogs for water. It takes roughly 100 grams of water to make 1 gram of sugar. It shouldn't take that many, and the reason is it's leaking so badly at present levels of CO2, which are so low. If you increase CO2 levels, plants don't need as much water, and that's why plants are invading dry areas. This is an example. This is Sherwood Itzo. Some of you remember Sherwood. He's still around, but he's quite elderly. But this is a pine tree. I think this was actually grown here in Phoenix, and it's an Edicara pine. And this was ambient CO2 levels at that time, and these are various enrichments of CO2. So you see it has a huge effect on the growth of plants, and that's true of just about any plant you try. Here's another one. Well, here's the actual experimental setup. You enclose them in containers where you can control the CO2. This was somewhere here in Phoenix. I'd like to visit it someday. And this is the response of various plants. Everything that you try, roots and tubers, potatoes, soybeans, fruit smells, all of them increase their productivity if you increase CO2 in the atmosphere. And someone mentioned greenhouses, and if you click on CO2 in greenhouses, you don't always find some alarmist message. You find somebody trying to sell you a gadget like this to attach to your actual greenhouse. And what this is a propane burner, and it takes the exhaust from the propane, which is CO2 and water. It throws away the heat, and it puts the exhaust into the greenhouse to make the plants grow better. It seems kind of crazy, but the cheapest source of CO2 today is propane. If you want to buy some CO2, it's much cheaper to buy propane and burn it than to buy a tank of CO2. Let's see. I mentioned that CO2 levels are extremely low now. Here we are today. These are parts per million. We're at about 400. You can just barely see it on this scale. And these are millions, hundreds of millions of years ago. So over most of geological history, CO2 levels have been measured in thousands of parts per million, not a few hundred parts per million now. And that's why plants are having such a hard time, is that plants are really used to these high levels of CO2, which have gone away recently. And they're struggling to make a living now. So if we add CO2, that will increase the productivity of the earth. Here's what's happening to the earth. I'm almost through now. So here are measurements of the increase of chlorophyll around the earth. You can see this rapid greening of the Sahel, the southern Sahara, greening of Western Australia, greening of Western India, greening of Western Canada. And these are areas where it's a little too dry for plants to grow comfortably, but with more CO2, they grow just fine. So arid areas of the earth are really booming because of the increase of CO2. And of course, production is going up. This is wheat production in India, I believe. And I was actually born in India. Wheat production when I was born there was this puny amount here. And now it's practically off the charts. Every year it goes up, you know. And part of this, of course, is from better varieties of wheat. Part of it is from fertilizer, but probably at least 15% is from more CO2. You can actually do the experiment. So, you know, if you got rid of all the CO2, brought it down to pre-industrial levels, the Earth would have a harder time feeding itself. Sea level rise, again, one of the exaggerations. I hope someone else will speak more about that. I don't have time to go into it. But the sea level has been rising since the end of the last ice age, but the rate of rise is about the same it's always been. So sea level rises, it fluctuates, but it's about 2 millimeters per year. This is emissions of various countries. So it doesn't, I think emissions are good, but it doesn't matter what we do because emissions are going to be dominated in the future by China, this red line here, and by India, which is also growing very rapidly. So Europe can do what it likes. I hope the US will be sensible, but it can do what it likes. And CO2 levels are going to continue to increase, and I think that's good. So I'll end with a quote from Schopenhauer, sort of a grumpy German philosopher. But he had said a lot of things that are right. One, he says, all truth passes through three stages. First, it's ridiculed. Second, it's violently opposed. And third, it's accepted as self-evident. And the truth that CO2 is not harmful but actually good for the planet, it's somewhere between the stage of ridicule and violent oppositions. So I hope soon it'll be at the self-evident stage. So thank you very much.